Most API authentication examples show you the happy path. But what happens when your server expects tokens in a custom header instead of the standard authorization field? You'll see exactly how to configure FastMCP's StreamableHttpTransport to inject API keys into custom headers like XAPI key, while keeping the connection clean and reusable. The pattern works for any non-standard auth scheme your MCP server requires. From FastMCP import client. From FastMCP client transports, import StreamableHttpTransport. Async with client. Transport equals StreamableHttpTransport. https://fastmcp cloud/mcp. Headers equals XAPI key. Your token. As client. Await client ping. This demonstrates the transport abstraction pattern with custom header injection, a common approach for handling authentication in network systems. The concept revolves around separating connection details from business logic, where authentication credentials are configured at the transport layer rather than being hard-coded into application logic. What makes this distinctive is how it cleanly isolates security concerns from the core client operations, allowing the same client code to work across different authentication schemes. The pattern works by encapsulating authentication details within the transport configuration, where credentials are provided as headers or auth parameters during transport initialization. This follows the principle of dependency injection, where the client receives a pre-configured transport rather than managing authentication itself. The approach maintains clean separation of concerns, as the client remains agnostic about how authentication happens, while the transport handles the specifics of token formatting and header injection. This approach matters because it solves the problem of authentication boilerplate while keeping security configurations flexible and maintainable. It's particularly valuable in microservice architectures, API clients, or any system where you need to support multiple authentication methods or rotate credentials without modifying core logic. The trade-off is slightly more upfront configuration, but the benefit is cleaner code and the ability to switch authentication mechanisms by changing only the transport setup. Let's break it down line by line. From FastMCP import client. This imports the client class from FastMCP, the primary interface for interacting with the MCP server. It handles connection management, request serialization, and response parsing under the hood. From FastMCP client transports, import StreamableHttpTransport. This imports StreamableHttpTransport, a specialized transport layer for FastMCP that enables streaming responses over HTTP. It's required when you need real-time data handling instead of simple request response, like for AI tool outputs or progress updates. Async with client. Context manager pattern with async support. The async with ensures the FastMCP client connection is properly initialized and cleaned up after use, preventing resource leaks. This is the standard way to manage async client lifecycles in FastMCP. Transport equals StreamableHttpTransport. This specifies StreamableHttpTransport as the connection handler, enabling real-time streaming of responses from the FastMCP server. Critical for tools requiring progressive output like AI-generated content or live data feeds, it prevents blocking while waiting for complete responses. https://fastmcp cloud/mcp. This is the FastMCP server endpoint URL. It specifies where the client should establish its connection, routing all requests to the hosted MCP service. Headers equals XAPI key. Your token. This injects an API key into the request headers using the XAPI key field. FastMCP requires this for authentication, and the transport layer automatically attaches these headers to every outgoing request. This closing parenthesis terminates the StreamableHttpTransport configuration block. It finalizes the transport setup before passing it to the client constructor, ensuring all connection parameters are properly encapsulated. As client. This binds the client connection to the variable client within the context manager block. The pattern guarantees proper resource cleanup when the block exits, preventing connection leaks. All operations on the FastMCP server happen through this client instance. Await client ping. This sends a lightweight ping to verify the FastMCP connection is alive and responsive. Critical first operation that confirms your API key and transport configuration work before making real requests. StreamableHttpTransport pattern. This transport implementation bridges FastMCP's async capabilities with HTTP's ubiquity, enabling real-time bidirectional communication over standard web infrastructure. The headers parameter completely replaces the auth system when specified, requiring you to manually handle all authentication headers. Always prefer StreamableHttpTransport for new deployments unless constrained by legacy SSE infrastructure.
The transport that carries no data becomes the channel for all messages.